This is an introduction to the module Discrete Mathematics, module code 251. It's a second year option available to the mathematics programs, although there's also a level 6 version available this academic year. Hi, I'm Simon Salomon. I'll be teaching the module. I've been at King's now almost exactly 9 years, and I've taught this module 3 times before. I was planning to teach a different module this year, but because of COVID, things have been simplified. So this will be my 4th year in charge of the module. I do research in geometry. Previously, I've taught the first year course Geometry 1, although that doesn't exist anymore. It was essentially a warm-up for geometry of surfaces, which some of you may be doing. And I also taught in the past a small course on game theory. So let me take you through the contents before I talk about 1 or 2 topics. So if you're looking at me, you've presumably found the Keats page, which is here. And you see there are 8 topics listed, which are covered during the weeks of the module. And it's really a mixture in terms of mathematical content. It's a mixture. There's some arithmetic and graph theory. Arithmetic at the beginning, quite a lot of graph theory and network theory, and then back to some linear algebra and arithmetic at the end of the course when we talk about codes and cryptography. So because of the graph theory, some of the course is explained in terms of pictures, but there are still quite deep mathematical concepts involved and some proofs to understand. So what I'd like to do now is just to give you a flavour of the course by covering a couple of topics which may be familiar to you, but they'll give you a taste for what's in store. So let me do that now. So the first topic I'd like to mention, because we'll be starting the course talking about recurrence relations. So the first topic concerns Fibonacci numbers, the sequence of Fibonacci numbers. And first of all, let me draw the table. Of course, they're very easy to work out. So for each non-negative integer n, there's a Fibonacci number, which we call Fn. And let's just first of all list the integers. I'm going to go up to about 12, I think, to illustrate what I want to say. And then the Fibonacci numbers, it's always arranged so that F0 is 0 and F1 is 1. That's very easy to remember. Then, of course, you just add up the previous 2 to get the next one. That's the rule for defining the Fibonacci numbers. So 0 and 1 is 1, 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5. Notice that the 5th Fibonacci number is equal to itself. Well, F5 is 5 is what I mean. 8, 13, 21, 34, 55, 89, and it should be 144. It's quite easy to remember under the 12. Those are the first few Fibonacci numbers. So the relation, if you haven't seen this before, is that if you like, the Fibonacci number Fn is equal to Fn minus 1 plus Fn minus 2. So this will be valid for n at least 2. But we have to specify the first 2 Fibonacci numbers. We'll be looking at lots of different recurrence relations of this type. The Fibonacci numbers are just one example. It's not actually the simplest, as we'll see in a moment, but it's a very famous sequence introduced by Leonardo di Pisa in about 1200s, about the time the Leaning Tower of Pisa was half built. In fact, he wouldn't have seen it completed. It was begun more or less when he was born, but he wouldn't have seen it completed. So let me tell you some facts about the Fibonacci numbers. So the first fact well known is that if you take larger and larger Fibonacci numbers and you work out the ratio of successive ones, so fn plus 1, for example, divided by fn, this tends to the so-called golden ratio. That's 1 plus root 5 over 2, as n tends, which is about 1.6, as n tends to infinity. We'll see a general formula for the Fibonacci numbers, which I don't want to write down now, but it involves the square root of 5, and it explains the ratio tending to this number. This is roughly. Of course, this is an irrational number. Quite convenient because this is also almost exactly the ratio of 1 mile to 1 kilometre. So if you're doing 89 miles an hour, you're probably doing about 144 kilometres per hour, which is probably too fast on most European motorways. It's also useful for this link and this link if you're on slower roads. It's worth remembering. Another way of getting Fibonacci numbers, not so surprising, you can get these from Pascal's triangle. So if we write down the binomial, instead of writing down the triangle in the usual way, we sort of we start with the ones against the wall, so to speak, and I'll start the Pascal's triangle 1, 1, 1. These are just the binomial coefficients when you expand 1 plus x to the power n. So squaring it, you get 1, 2x, x squared, 1, 3, 3, 1 for the cubes, 1, 4, 6, 4, 1 for the fourth powers, and so on. 1, 5, 10, 5, 10, 10, 5, 1. And if you just add these up diagonally, you get the Fibonacci numbers. It's probably not so surprising if you know the rule for Pascal's triangle. But you see you get the 1 and 1 is 2, 2 and 1 is 3, 1, 3, 1 is 5, 1, 4, 3 is 8, and so on. And you're getting the Fibonacci numbers down here. These are the Fibonacci numbers. But that tells you that the Fibonacci numbers, each Fibonacci number is a sum of certain binomial coefficients. So there's a link with binomial coefficients. This course will help you revise things like the binomial theorem and consolidate other things you've learned in the first year. So let me now tell you something else about the Fibonacci numbers, which is slightly off the scope of the course. I'm not sure we'd be proving this in the course. But I want to explain that the Fibonacci numbers are closely related to greatest common divisors. And in fact, we'll be using the Fibonacci numbers to understand something about Euclid's algorithm. So there's a very intimate link with Euclid's algorithm for the greatest common divisor, which you probably learned about, hopefully you learned about in the first year. So just remind you, this is for finding the greatest common divisor of two numbers. I'm not going to talk about this. I just want to say that they're related. So let's just say somehow related to the Fibonacci numbers. And let me try and say why that's related, or why the concept of the greatest common divisor is related. And to illustrate this, I'm going to choose a couple of Fibonacci numbers. I'm going to choose F8, 21, and F12, which is 144. And I'm going to ask you, what is the greatest common divisor of these two Fibonacci numbers, F8 and F12? Well, that is, of course, the greatest common divisor of 21 and 144. 21 is 3 sevens. 7 does not divide 144. So the greatest common divisor is 3. 3 does divide. This is divisible by 9. So 3 does divide 144 and 21. It's their greatest common divisor. But 3 is as well a Fibonacci number. It's the fourth Fibonacci number. And it's not a coincidence that this is actually for is the greatest common divisor of the two indices we started with, 8 and 12. So this is an illustration of a very famous result that says the greatest common divisor of two Fibonacci numbers, say f depending on integer a and f depending on integer b, is actually a Fibonacci number, and it's the Fibonacci number associated to the greatest common divisor of a and b. And that's actually a very important fact. It's a good idea to know this. I'm not sure whether we'll actually prove it in the course, but we'll certainly use the Fibonacci numbers to talk about Euclid's algorithm and understand that Euclid's algorithm is very effective. It can be implemented in what's called log time. The number of steps needed to find the greatest common divisor of a and b is related to the logarithm of a and b, so it works very quickly. Okay, that was my first illustration, and Fibonacci numbers are studied fairly early in this course on discrete maths, although we spend quite a lot of time in the middle of the course talking about graphs and graph theory. That's sort of configurations of edges and vertices, and the combinatorics of that. And then we start putting numbers on graphs and talking about what are called weighted graphs. We talk about minimal spanning trees, finding a way of linking the vertices of a graph so that the total weight is minimal, or the shortest path between two vertices of a weighted graph, that's sort of the sat-nav problem, or not so far removed from the sort of algorithm that's used in Google Maps, for example. So we'll be studying that. Some people you probably know about Dijkstra's algorithm, which is used for that. So there's a mixture of theory and algorithms which explain how to solve problems in practice. We'll also be talking about networks in which we have graphs with both arrows on the edges and also numbers. And we try and find flows from one vertex, so-called source, to the sink of the network. And then at the end of the course, we'll be going back to talking about arithmetic, well, actually more linear algebra, but working modulo 2 to talk about binary codes, and finally finish with some properties of prime numbers to talk about the famous RSA algorithm.